Hey everyone, I am going to go through section 8.2 information with you, which is on temperature scales. And before we get there, I just want to take some time to review our previous section with some different pictures that are a lot like the elements, compounds, mixtures, POGIL you performed. So taking a look at these, you want to be able to identify, is it an element, is it a compound, or is it a mixture? Could it be a combination of them? So if you want to take a moment and pause and take a look at each of those photos and try and identify what you think is an element, compound, mixture, or what combination could it possibly be, go ahead and do that. Otherwise, I'm just going to zoom right through and talk about each of them. So right here, we have all the same empty circles. There are no additional components. They aren't directly attached to anything. So I would call this a pure substance, aka an element, right? Same atom, same type of atom, nothing additional to it. The second image here, we have black spheres and we have empty spheres, and they are physically touching each other. So there is a bond between them that's happening. And we have two different types of atoms, right? Black, white, bonded together. So we must have ourselves a compound, right? And we can see that each of them has one of each, and there's not anything different combining there. Over here, we have white spheres, black spheres. They're not touching each other. So we have two or more atoms that are not chemically combined together. So this would be a mixture. Okay. Over here we have, again, what looked like the same thing as our second picture, and our empty spheres like the first picture. The three of them are not touching each other, so we know we have a compound, and then we know we have single atoms over here. So again, this is going to be a mixture of an element and a compound together. And then the center one here, bonded together, two or more atoms. They are the same type of atom, so you could still call this our pure substance category, and you could call it a compound because they have a chemical combination to them. And then our last one over here, so this would be like oxygen gas, we could call that oxygen gas over there. And then this third one we have, be careful, we have our Mickey Mouses over here, right? And then we have the dual ones next to each other that are combined together chemically. So we have two chemically combined compounds in the same area with each other. So this again is going to be a mixture of two different compounds. Hope you able to ace that thing. All right, moving on. Oops, I forgot that I even labeled these for you. Mixture of elements, mixture of an element and a compound, argument for element, or it could be a compound mixture of compounds. Okay, so if I get myself out of here for a moment, these are our different learning targets for section 8.2. So we're going to be looking at temperature scales and energy and how they are all related. So by the end of this, hopefully you can answer. I can convert between Fahrenheit, Kelvin, and Celsius. So we're going to do some calculations. I can explain what thermal energy is and how it applies to our temperature scales. I can explain what temperature is, and the last one is, that out of the way, I can explain how thermometers function. So I wanted to grab this here to talk about our thermal energy or kinetic energy as well, with this. And I'm just going to mute it because we don't really need the sound. They're just adding food coloring, and there's hot water, around 90 degrees. And then this one over here is around 20 degrees for our cold water. And you can see the instant differences once that food coloring, not blood, I promise, was added into the water, right? And we know that kinetic energy is the energy of moving things. And in this case, when we talk about temperature, the higher the temperature, the more kinetic energy the molecules have, meaning they're moving around faster, they're bouncing around and colliding with each other at a higher rate versus the colder water, which is on the right side here. We can see that they move around or they have lower kinetic energy, and they are not bouncing off of each other as quickly. So we can see within our given time frame that our hot water and our red food dye has almost completely mixed together because those molecules are moving fast and they're spreading the color all the way around the entire glass. Whereas by the end of the cold one, we can still see that the molecules are moving slowly, so they haven't quite been able to pass along the red food coloring all the way throughout the glass. Hope that makes sense and ties back to our chapter 7 information we covered last quarter on kinetic energy. But here it is again. So remember, kinetic energy is going to be related to our thermal energy. It's the energy of motion. And anytime something's moving, it's going to be giving off a little bit of that energy as heat. So no matter what, atoms are going to be in constant motion. So even if they're solids, they're going to be tightly packed together. Like we saw in 8.1, they're going to be really close together, but they're going to vibrate back and forth. So they have their bonds that hold them in place, but there's going to be still some vibration, which is kinetic energy and thermal energy. And then we can see here, just like the video I gave you, heat can be transferred between those areas. And so when there's high temperature, they're moving a lot faster and colliding with each other. When there's lower temperature, those molecules have lower kinetic energy or moving slower, less collisions. All right. So what is temperature? Temperature is the measure of kinetic energy per molecule due to the random motion of those molecules, right? So this is really reflective of what happens to our molecules for whatever object we're dealing with, right? So they're randomly moving back and forth. Temperature, when we find the temperature of that object, there's that random motion, which is an important piece to add to your definitions if you don't have them already. And then we can see that there's average motion of the molecules, but when that temperature is increasing, it's going to, force the molecules in our thermometer to move, and they have no place else to go but up in our thermometer. So that's why we get our thermometer reading as it goes higher up. That temperature is increasing because there's increased kinetic energy. Hope that is making sense. Oops. So here's the reasoning behind our thermometers. As we talked about, truly it has to deal with, again, density, which we haven't quite talked about yet, which is chapter 10 material, but we can connect it to our kinetic energy piece of once they're moving around, they have to move somewhere. And with our thermometers, there's limited space and there's an opening for the red dye or the red alcohol to rise in the thermometer. And then when they cool down, the temperatures cool down, the molecules slow down and they start to condense, and then they start to push back down towards the bottom of the thermometer. I'm going to skip that one just because. Temperature scales. It would be beneficial for you to know the connection between Celsius and Fahrenheit. And yes, we live in our world of Fahrenheit, but we know the rest of the world lives with Celsius. And why do we have two different temperature scales? Because when Sir Fahrenheit came out with his temperature scale, he was actually dealing with salt water and didn't realize that there would be much of a difference between salt water boiling, freezing, that sort of thing, compared to when Celsius came out and they were measuring pure water, no additional substances included. So that's why we end up with this kind of silly different scale of Fahrenheit and Celsius, although we can have temperatures that tell us what happens to water when it freezes at room temperature, normal human body temperature, boiling. The scales are different just because we were basing them off of salt water versus pure water, which is kind of annoying. I really like Celsius because we go from 0 to 100, from freezing point to boiling point. But if you ever are asked, what's your normal temperature? What's room temperature? You could probably answer that really quickly with Fahrenheit, and then you'd have to think about it or Google it if you were answering that question for Celsius. So additional piece on there, there's another temperature scale that is called Kelvin, and that's going to focus around this definition called absolute zero. So molecules are constantly in motion, right? They have their kinetic energy. When their temperatures decrease, their kinetic energy slows down, so their vibrations and movements slow down. The point at which molecules stop moving and atoms stop moving, that's called absolute zero. And its connection to the Celsius scale is negative 273 degrees Celsius. So if we're thinking about like temperatures on Antarctica, which was in your book, absolute zero is much, much colder than that. Here's another connection between the Kelvin scale versus our Celsius. So again, they can both show us where that absolute zero scale is. But we know on the Kelvin scale, that's going to be 0 Kelvin. And over here, it's going to be negative 273 degrees Celsius. Freezing point is 0 Celsius. Plus 273 gives us our freezing point, right? So if we just keep adding 273, we get our information over here for the Kelvin scale versus Celsius. Just wanted to show you how those are related to each other again. All right, I'm going to stop there. I will be adding in an additional video on how we convert between temperature scales, and you will be doing some calculations along with that. Please make sure you go back, and if you had any questions on, here, our learning targets, there are pages here that you can go look back at your book for further information. See ya.